Is my recording not starting? Okay, my recording started. So chapter 5, I go to the notes again. Look, let me make this a bit bigger. Is it better if it's a bit bigger like that?
Yes.
Yes.
I'm sorry, it was a bit small, eh? It was a bit small all the time. Yo, how could you see such small things? You must tell me immediately. You're allowed to talk anytime, eh? You can talk, people, you can talk anytime. You can ask me anytime. It won't disrupt. Eh? What is that? I can't hear you properly. Okay. Someone said something, but I didn't follow that. People, the chapter 5 is about fiber connections and joints. How do we join it? How do we join this fiber? How do we make a much longer fiber out of it? Also, couplers and isolators. Remember the word coupler and isolator. Those two things, you must know what it is. If I ask you what's an isolator in a test or a coupler, we'll get to it. But we'll do fiber alignment and the losses, fiber splices. That's actually how you join it. Fiber connectors, expanded beam connectors, and fiber couplers. And in isolators and circulators, you must know what this is as well. Right, let's begin. This is an introduction. I'm going to just skip that. And I want to tell you that when you join fibers, there are a lot of losses actually. So when the two fibers are joined together, you see here, even when it's smooth and perpendicular means it's 90 degree or 180 degree exactly, even then there are some losses. A small proportion of the light may be reflected back to the transmitting device, which is the laser or the LED. Usually I talk about the laser, which is the source. The laser is also called the source, okay? So people, some of that light that the laser gives to the fiber, it doesn't go into that fiber, all of it. Only about 10% goes into the fiber. Did you know? Because that fiber in front has got a 90 degree mirror. And it's very, very, very much like a glass mirror. And only a little part of the light goes into the fiber. Most of it comes back. It reflects back to the laser. And it damages that laser. What it also does, it not only can damage it, it can also cause the laser frequency and modes to mix up with each other. So just a little background information about this and why we're doing this stuff, so that you understand. Now this phenomenon, we call it fractional reflection. This fractional reflection is really, it's a mirror there, and the light, not all of the light goes through, some comes back. When you look in a pond of water and you see yourself, that image of yourself, that's called the fractional reflection. When you look down into a dam of water, you'll see yourself there. Fractional reflection. We must know the word. The classical Fresnel formula, we can calculate that reflection, okay? How much of your face do you see in that water? And how much does the fish see? The fish swimming around in that water. Okay, the Fresnel reflection is what you will see. So, reflection value is the N1, the core value minus N. N is for the air, okay? Now for air, it's usually a 1. So it's N1 minus 1. And then N1 plus N, which is N1 plus 1. So you square it and you've got the Fresnel reflection value. So here they say N is 1, which is for air, and so on, because we go from air into the fiber. However, people, if this fiber was inside water, we will go from water into the fiber. So N will not be a 1 for water. N for water will be maybe like, I don't know, maybe 0.9. It'll be given to. I'm just mentioning how this N works. So it's a mirror basically going from air into the fiber. Now the losses in the fiber is, the Fresnel losses is minus 10 log 10, 1 minus R. So you take that R value, 1 minus R is here, and you calculate the losses. You must know this formula. You must know the fraction of formula. So this is just a numerical value, the numerical ratio. They call it in math the numerical ratio. Do you still remember your math numerical ratio? However, this is a dB value in decibels, this value here. So the decibel value, this is how you calculate it. Because I might ask, what is the losses in decibels? Not the numerical ratio here, R. Okay. Now R is the fraction of the light reflected. You see there. That's your face that you see in the water when you look down to the water. R is your face. Yes, you've got an R face. No, just a joke. Right, so you can do this example. Please mark this example. You must know this example and work through this example, because this tells you how the Fresnel losses work. Right. Now, I'm not going through the example. Do you have any questions on this? Okay. Then we've got other ways and places where we've got losses for the fiber. There's about 5 of them, but I'm going to show you now 3 of them. These 3 is the longitudinal misalignment, when the fiber is a little bit distant from the other fiber, and you join the 2 fibers, but there's a gap there. You see that air gap? It's longitudinal misalignment. There's a formula for it to calculate how much will the losses be. Then for this one, it's a bit skew here, you see, in a lateral direction. So this one is a little bit skew on that one. So it only covers the joint by about 70% in this case. So this is called the lateral misalignment. Lateral misalignment. You must know this picture, guys. I will ask it in a test. So laterally, longitudinally, and also angular misalignment. Number C. Now this is when I've got an angle there. So my light ray doesn't go like straight through here. There is a misalignment here. So my total internal reflection will be less. It will be scattering a bit here. So now also other things that contribute to losses is different core diameters. If my core diameter was different here on this one than here, say this core diameter was bigger, then it will not be aligning so nicely, and it will also cause some losses over that. Okay, another one, different numerical apertures. So if this fiber has got a different NA than this cable, the NA of this one is, say, it's 0.2. The NA of this one is 0.3. People, you cannot join fibers with different NA. You can try it, but it'll have a lot of losses. Just remember that. So it will work for a short distance, but there will be some losses. Number C, different refractive index profiles. So if N1 is 0.4 there, and N1 is 0.6 here, it's got a different value for N1. It will cause losses. So that's not a good idea. Alright, fiber folds. Maybe the core is more elliptic, or the concentricity is not so well. So if it's elliptic, it's like almost, it's not circular. It's like ellipse like that one. And this one is now circular. Imagine the diameter is smaller like in this direction and bigger in that direction because it's elliptical. Then you will have a lot of losses because the cores are not the same. They were manufactured from different cables, so it's not a good idea to join them. But if you join them, if you really want to do it, you can do it. Then just remember your losses will be more. Okay. I don't have formulas for these four, but I've got formulas for these three here. We'll get to the formulas now. So we'll talk in detail about this now. But you can see here, people, there are 7 things causing losses. Do you see the 7 things? The 8th one here is really the Fresnel losses, okay? So it's 1, 2, 3, 4, 5, 6, 7, and then also the 8th one, which is the Fresnel one here. So add it to the one, to these ones to get your total losses. So each cable, when you join it, there are a lot of losses for it. Okay. Right, I'm going to carry on and skip a lot of stuff here until I get to multi-mode fiber joints. It can have also lateral, angular, and longitudinal misalignments, and there will be losses, but I'm not going in detail into that. I'm not going to do this formula, but you can look at this formula here. This formula, you can look at this. So the losses, the lateral losses is this one. There's another one, 5.5. And then you can really do this formula in this example 5.2. So step in Ch5 with this, I'm not going to go through it, you guys can go through it. So in this one you can calculate your lateral losses. And actually it's called the coupling efficiency. Coupling efficiency. Look at the formulas. The formulas is 5.3 and 5.4. It says here, those equations are the ones above here which I showed you, which are these ones. So include this one. Sorry, I made a mistake. Just include this one. Alright, so do that example. And here, I'm going to skip this example. I will not ask you this one. This is for the graded NX fiber, which is just the same as for the other one. But I'm going to leave this 5.4 example as well. I'm going to leave it alone. I'm not doing it. However, we're coming to figure 5.3. You can see now that when a one core diameter is bigger than the other core diameter, you see here, you can expect losses here. Also in this case, where the numeric aperture is differently, this angle of acceptance will be different. You see, it's not the same. And that means there will be some losses here. Also, the profile difference for a multi-mode fiber. You see, alpha 1 and alpha 2 slightly different. This will cause some losses as well. I'm not going to go into those losses here with this formula. I'm not really doing this one. I'm not doing those as well, but you can calculate the losses for the NA for all 3 of these. So I'm just looking at the figure and not the formulas here. Single mode fiber joints, let's look at this. You must know this formula. It's here. This is losses due to lateral offset. Now, remember there on top, those 3 pictures just now, the lateral offset was there. So you can use this formula to calculate where omega is the normalized spot size. The spot size here And the omega you can calculate here. To calculate the spot size, you can use this formula. And I think we had it 2 weeks ago also. But it's basically this one, that is minus 3 over 2. And let's just do a minus 6 there. And that is 2 half, which is the square root. So just remember the formula is very fixed there. It's fixed there. These numbers are fixed. And you multiply those with the, I think A is the radius. That's not the diameter. People, if I give you the diameter here in a test, I'm going to catch you because it must not use the diameter here. I'm pointing it out to you because that's what I do. I give the diameter here and then you come and you put the diameter in there. Then this one is wrong. So calculate your normalized spot size, omega, put it in that formula, and then you've got your losses here. And that loss is actually already in dB. You don't have to say 10 log. It's already a dB value in losses here. Okay, that Y is the lateral offset, okay? It's all written here. So look at this page. And this one is the angular losses. Sorry. This one is the angular losses. So the angular losses, it's also in dBs, is your angular misalignment value and insertion losses due to angle misalignment. So if I ask you to calculate the insertion losses, you see here, and lateral losses, I can give you these two formulas. You have to calculate that. Right, I'm going to skip. There's an example. And look here, I've asked it twice in previous exam papers. So you can see it's important to go through this one. Go and work through this example 5.5. It tells you how to do different losses, and then at the end what I tell you, that if I ask you the total insertion loss, don't give me that one, that's only for angular misalignment. Then you must add those two losses up here to give me the total value. Do you see? So all two together will be added up to form this value. I'm going to skip this example, I'm not doing it. Example 5.6, skipping there. And we're coming to fiber splices. Splicing fiber means how to join the fiber, really. So we've got mechanical splicing, and then we've got fusion splicing. These are the main two types, people. If I tell you to give me the main two types of splicing, most people cannot do this, but it's in this paragraph here, it's written. Fusion splicing is when you apply it with heating. Mechanical splicing is when you hold it together with a joining. So that's fusion joining, we melt it. This one we don't melt, we just hold them together right across each other. We just hold them there mechanically in a clamp. Alright, let's do it in detail. First thing, when we want to splice a cable, we take a knife edge and we make a crack in the fiber there. This is a mandrel. We curve it over the mandrel and we give it a cut here. It's going to break off very squarely a 90 degree here at this point. So we cleave the fiber. We call it cleaving. And then what they do is they make it smooth and square at the end faces. So you sand it down squarely, and you put it in a holder, and you make it very, very square, because that angle must be 90 degree to the fiber, very much. That is a mirror, and that mirror must be very clean. So you sand it down with very, very fine sanding paper. So you can read this whole paragraph for background. Fusion splices. That is now when we melt it together. Okay, how do we do it? It's like this. They've got two electrodes on the side of the fiber, and they've got two mechanical clamps, one here and one there. Okay, they will align these two blocks to each other. They will align them. And your eyes can't do it because you will never with your eyes see that, but they can do it by shining light into here and see how much light comes out, and they align these two perfectly. And then they press them together there, and they melt it with these two electrodes with the electrical arc. So there's your fiber which is joining, and I melt it with an arc here, and it's square. It's arc fusion. With an electric arc, they arc it, and it's joined. The fiber is joined like that. Not so perfect like here, but almost perfect. Right, that's mechanical. Oh no, sorry, that is fusion splicing. In this case, what I do, they hold the fibers next to each other, but not very well. You can do it with your eyes. You align it almost precisely there. Then when you give heat here at this point, it will self-stretch, and it will connect like that at first, because there's surface tension here. The surface tension will make it straight. It will straighten as soon as you melt it. It will straighten out, and there will be a small error there, but it will be a good fusion alignment, self-aligned splicing here. So you can check out this picture. You can just make sure you know this picture also 5.6. Now we're getting to mechanical splices, alright? It's a common method where we align the two tubes, and then what we can put them to align them, we can put them in a ceramic capillary, just big enough for those fibers, and we join them with epoxy there. They take epoxy glue and they seal it mechanically. You can use this machine also to do it. The machine will do it automatically for you. The new machines look different, but this picture shows you how its alignment is. So it's a camera, and it's enlarging it like 100 times, then you can see what's going on. And this machine will actually do the splicing for you automatically. That's a handheld device that also does it. Right, let's see how it works. They take the fiber and they put it in a little capillary tube. You see that tube? A little metal tube. They put it in there and it will be aligning there. To align it properly, they will have a square tube, and they will align it in this corner. You see that corner? It will go into the corner and it will align properly there. This picture and how they do the alignments. Also what we have is V-groove alignment. You can read this stuff here, V-groove alignment here. They talk about it, and they fill up with epoxy resin after the V-groove join. Okay. The losses here is typically 0.1 dB, which is very little. But there are losses when you join. Okay. This is a V-groove. This is how it looks. I've asked it in that exam. By figure 5.9, you must know it. The V-groove method. It's a V-groove there. You see the V? That V. It's a little groove there. This is very small, people. This is like half a centimeter by half a centimeter. It's a little V-groove. So what you do, you take the fiber, you put it in that corner, this fiber into that corner, and you put epoxy and glue in there. You're going to glue this thing together. And what you do is a little flat top. There's a lid, you put it on top and you clamp it. The glue is now in there, it's joined. The V-groove will align it, so you could join, you've aligned this fiber. This is another one. It's a elastomeric splice. What you do here, it's a little tube like that. Also very small, 1 centimeter long. And then you put, there's a little hole in the middle with a cone here to help you finding the hole. Otherwise you'll never find that hole. And there's a cone cut out there also. So you put the fiber in the cone cut out and it will go into the middle. You put some epoxy and you are done. It looks like this afterwards. And then there's a spring groove. What I do here, they take 2 cylindrical pins here. They put the fiber on top, see, and I put a little lid on a spring. The spring looks like this. So they put it on top, and this whole fiber will be very well aligned here, and they will glue it together with epoxy. So the V groove and a spring groove and the cylindrical splice here. The 3 types. You must know those 3 types. You must know these pictures. How to splice a fiber. This is how to splice it with capillary tubes. So there's your capillary tubes that we talk about, your cylindrical sleeve, okay? And what I then do, this fiber comes in here and it ends in a glass ferrule there. This fiber comes in, it ends in a glass ferrule there. And what I do, they just put it together with a little sleeve here, and I join the 2 fibers. This is how it looks inside a connector, because now there's no glue here in the middle and you can still separate the 2 connectors from each other. You see, so you can unplug your box here, but the glue is usually inside this part. They put the glue inside that ferrule, and that ferrule they will put epoxy glue in there also, and the connector will join it. I'll show you another connector now. Okay, this is another way of splicing it. They've got a little off-center hole there and an off-center hole here, and I will turn them until they align there. It's another clever way of doing splicing with 2 ferrules. I call this a ferrule, and that ferrule there, and I will align them by turning them. It's not so important, but I'm just showing you for the interest sake. There's different ways to splice and join fibers. Multiple splices, people, that's if we must do more than 5 or 10. What we will do here, it's almost like a ribbon cable. There's your ribbon with maybe 10 fibers. There's the 10 fibers. You clean the plastic off here, okay? Then you've got a silicone chip at the bottom with grooves in it. You've got a silicone chip on the top with grooves in it. And what you do, you push the ribbon in this side and the other one from this side, and you clamp it with these 2 top and bottom silicone chips. It's very small. It's like 5mm by 6mm, this one, or even smaller. But you can join 10 fibers or more with this. It's actually a 12 fiber splice, what we say here. You can have this type V groove polymer resin where you've got another 10 or 12 fibers there, another 10 fibers here on a flat cable ribbon coming in. You must join them here. How do you join them? You put them in this clamp mechanism with grooves at the bottom, and that one has got V grooves on top, and you just clamp them in, and afterwards you put the steel clamp on it, and you put the steel clamp on from this side, and the steel clamps will hold the whole lot together. And then what you'll do, you'll put epoxy glue there in the middle and it will be joined. Right, fiber connectors, that's another way to do it. We've got cylindrical ferrule connectors. I'll show you a picture. I've asked this before, so you must actually know this picture. 5.16. This picture looks like this. It's a connector. It's two halves. There's your fiber coming in, and it's onto the connector on the left-hand side. Then the connector on the right-hand side, it's got its own fiber there coming in. It will be joined right here in the middle. This connector will have two ferrules, and they will be lining up perfectly mechanically inside the connector. You buy this connector. People, this connector, it costs about 800 Rand if you buy this connector. But you can buy it, you can join fibers with this connector. You can unplug it again. Now that ferrule inside there, how it's done there, and that ferrule inside there. This is the picture for that ferrule inside there. This picture, you must know it. How it works. That ferrule is now blown up. It looks much bigger here, but it's got a little hole in the middle, a little tunnel. So you put your fiber in this tunnel, and you put epoxy glue there. You see here at the point, just a little bit of glue there. So it's a stainless steel ferrule with a little hole in it, and you put your fiber in until it's going through here. And then what you do when it's dry, they actually put a watch jewel here, like a ruby. A ruby helps to guide it, and it's very accurate. So the ruby will sit there, and they will glue it onto that point. And then they will sand this thing off 90 degrees. And they will make a mirror with very, very, very fine sandpaper. They will make a perfect mirror, 90 degrees, with respect to the fiber. So that little mirror there, that small little mirror, will be 90 degrees to the fiber. And that's where your Fresnel losses will happen, right there at that middle spot there. That's where the mirror will be. Okay, so this is a ferrule connector. I'm showing you other ones as well, but I'm just showing you this one now. This is how you, and you can unplug this connector again to move your box to another room. You can unplug it there, and in that room you can plug it in again, some other cable. That's very nice, but the losses here are a little bit more than when you melt it or when you do V-groove or cylindrical joining. The losses are a little bit more, but it's not too bad because we can actually remove the cable here, unplug it. You can read this in blue. This is another one. This is an ST. You see the ST plug? ST plug is this little bayonet here. You see that bayonet here? And the bayonet there. So what you will do here, you will take your fiber, it will end here in this thing. It will be glued in that ferrule there. And then you put it into this mechanical connector. There's a lock nut here, and you will lock it. And this, you see this, will lock into that one like this. So this is an ST connector. You get SMA connectors here on the sides. You get all kinds of connectors here. I'll show you just now. You get this one also. It's a full duplex fiber connector. There's two fibers, and I can join two fibers at a time. This little plug into receive and transmit. You can join two fibers with this connector. It's just other ways to do it with multiple fibers in a connector can be done. This is how they do it. You don't have to know this picture. I'm just skipping it quickly. And here you can see there are other connectors like a SMA, like I've said, a FDDI connector, a D4 connector. That's an ST connector with a bayonet there. This is a SC connector. Simplex and duplex, one cable and two cables. You can do both here, but mostly we do one at a time. It's your FC connector, your MU connector, your LC connector, your E2000 connectors. People, they are all different, but I've seen this E2000 a lot on the lasers lately. They use this connector for the laser. It's got a little plate there to protect it against dust, and when you press this button here, it lifts up that plate, and the fiber is exposed. You can join it in with another connector. This is a type of connector that I plug directly into the laser module. It looks like this. Then you get the MTRJ connector, MTP connector. And guys, do you want to learn all the names? No, I'm not going to ask you any of these names. I'm just showing you what they are and what you get. You get hundreds of types. You can't believe it. And look here. Do you see the sizes are all different? And the losses, sorry, not the sizes, the losses here. They give the losses for each one. If you want low losses, you choose here, like this one. Like I said, this one is also very popular, as well as this one. Losses are very low. See, those are the losses. Right, I'm done with it. You don't have to know these pages. What I'm showing you now, you must just know that there are other cable connectors which we don't know of. We've never seen them. We rarely see all of them. We see usually one or two types these days. Okay, expanded beam connectors. How can we align these things? It's very difficult, man. And you know, when you align these two little fibers, it's very, very difficult, and alignment's not very good. So what happens? The signal doesn't go nicely through. It's big problems, people, big problems. So what we've done, they've made little lenses. You see this lens here. You put it inside your connector, and it will have a point here, a converging point, and it will go into the fiber, the light here. So light comes from here, go to a wider light beam. You can easily align those because from there to there is about 2 millimeters. That's about 2 millimeters. Eh? So you've got 2 meters in where to align it. So all you do, you push the fiber in until this point, and then you glue it. You push that fiber in until that exact point of converging there, and you glue it. Now it's fixed. And then you can shift this point a lot up and down, like half a millimeter. It will still work. And you'll get very good mating and very, very little losses. Expanded beam connectors. I think you must know this one. What is an expanded beam connector? The next one I'm going to talk, micro lenses. I'm not going to talk much. They put little round ball lenses in there, in the connector. People, this is 1 millimeter small. It's very small. But they are round lenses there. And it works like this here. It will have a diverging point here and a converging point on that side. So the thickness of this connector is about 6 millimeters from there to there. So it gives you an idea. This lens is only about 1 millimeter big. You don't have to know this picture. I'm just showing. And a lot of other things. Okay, something that you must know is Grunrod lenses. What is a Grunrod lens? A Grunrod lens is a collimation lens. You see the word collimation. And it's basically a graded index lens. It's a graded index lens with collimation. What does collimation mean? Man, it's another English word. You know, I don't even know what you'll call this in Zulu or Sotho. They will have some other explanation, but these words are not translatable even in other languages. They just call it a collimation. So you must just learn the word, okay? Because I can't translate. Collimation means basically you put in light that is not focused at the right point. In collimation means you can focus that light on a point. But collimation also means you can, even when the light is like oval shaped, okay, a collimator lens can make that oval shaped light can make round. Even like if you have a light beam that's like shaped like almost like a triangle, okay, you can make a collimator lens that will fix that light into a round spot. Because in fibers we need a circular light, okay, a round spot. We don't need other patterns. So this collimator lens is doing all of that. So it does a lot of different things. It is basically a cylindrical glass rod you see here, and it's typically 0.2 millimeter big, but up to 2 millimeter. Do you see how small these lenses are? They are very small. Sometimes we can't almost not see them. So you can work with tweezers to insert them. You can work with a magnifying glass and so on. Look here, a granite lens can produce collimated outward beam, you see there, with a divergent angle alpha of 1 to 5 degrees. You can have up to 1 or 2 degrees here, people. That is very good. It means your losses will be very low with this one. Okay. Right, there's some formulas for them. I'm not doing the formulas. You are lucky. This is a collimator lens. Right, there's 3 types of lenses. I'll talk to all 3 now about them. But let's do the first one. This lens, it's got a certain length here. You see there, 0.25 pitch. Do you see there? That is the pitch of the signal. So, with 2.25 pitch, we get a 0.29 pitch as well, né? And a 0.23 pitch also. So, I'll talk to those 3, talk to you about that now. But basically, we've got 50 micron coming in. This size is 50 micron. Then we go to a half a millimeter here, the lens size, and it will diverge the light from this light. It will diverge to sort of an almost parallel light here. So the collimator lens makes this light here, a parallel light. And then we're going, it translates from 50 micron in light to 1000 micron light here. People, 50 micron in input light is like your hair, okay? 1000 micron is about 1 millimeter. So the beam will be 1 millimeter big. You can easily align this side, okay? But let's look when we put 2 collimator lenses together, we got a beam right through it. Next one. Here it is. There's 1, 2, 3, 4, 5, 6 pictures. You must know these lot. Picture 2.25, 5.25, and let's start with the first one. The first one is a quarter pitch lens. You see there, quarter pitch lens, and then a 0.23 pitch lens, and then a 0.29 pitch lens. You must know these numbers. You must know the 0.23, 0.29 pitch, and let's start with the 0.25. So light comes in here parallel, and it goes there to a point. The fiber sits right there. Fiber sits right there, and then the light goes through the lens. So this lens will join to that lens. We'll join them together in series, these 2. And this one, the same story. In this case, can you see there's a distance from the fiber to the lens? You see that distance? That distance is 0 here. But here it's some distance. That's why it's a 0.323 pitch. So your 0.23 pitch is there. So 0.25 will be up to this point. And there's a little air gap here. They've got this air gap so that it aligns better. Because you can never find that exact point on a fiber. It's very difficult. So they align it a little bit outside the lens. That's what they do here. And then the 0.29 pitch, they've got 0.03 there and 0.03 there. So this is 0.29 pitch. So in this case, the fiber is very close to the lens. Then it goes through the lens. It's one lens, and it goes through to the lens. There's a little distance here, as well as another distance here. So this is a 0.29 pitch method. Okay. You must know this picture. All right. And they explain here. This is the picture on top, and they explain it here. The focus is collimated outside the lens at 0.23. 0.29 also Both focals are outside the lens, do you see? But on the first one, it's inside, it's not outside the lens. Here, it's just on the edges of the lens. 0.25 pitch. It's outside the lens, the focus. Outside the lens, outside the lens. That is why we've got different pitches here. Guys, you must learn the stuff. Figure 5.25. Please know it. Fiber couplers. Right, we can couple fibers this way, but we can also couple fibers this way. Do you see? Sideways. Okay. So, in this case, they will react to each other with the surface here. In this case, that mirrors the Fresnel mirror there. But here, sideways. No. When we use that one, this one, we can have 1, 2, 3, 4 ports. They call it 4 ports. This can be a 4-port connector. This one doesn't have ports, okay, but this one has 4 ports. How does it look? Now we're coming to it. What we can have a 3 and a 4-port connector and a signal splitter. We can have star couplers and we can have wavelength division devices. But you don't have to know these points, I'm just highlighting them to you, what you can have. Now I'm going to get to them in detail. This picture, you must know this one. This is a 3-port on top, a 4-port and a star. If I ask you, show me all the different connector coupling for 10 points, 10 marks in the exam. This is a 1 to 2-way splitter. It splits up the signal. The fiber signal comes in and it splits up into 2 light beams. This one is a combiner. We can combine the 2 light beams. And then we've got a 4-port coupler. You see this one? It's port 1, port 2, port 3 and port 4. This one here, 4-port coupler, is this one here. I'll get to it later and there's a formula you must learn here. I'll show you now. So just know that there's also a star coupler where you can have 30 fibers to 30 fibers. And then a funny one. There's a wavelength multiplexer. This one will put 2 colors in here, green light and red light. It will mix, you'll get red-green light. Have you ever seen a red-green light? People, I've never seen a red-green light. But that's what you're getting out here. Combination of red and green. Or blue and how about pink? Lambda is the wavelength, so it's a different frequency of light. It means it's a different color. But look, you can get shades of infrared. There can be infrared very low frequency and the infrared a little bit higher. So it stays red, it stays infrared. Your eyes can't see it, but it's got different frequencies. We can mix them and put them in one fiber. Then we've got a nice thing here. We can split them in green light and red light. We can split it again. That's very clever. So people, you can put 20 colors in here and you can get 20 different colors out there. You can have 20 cell phones on this fiber in talking to each other in different colors. And at the output you can have your 20 cell phones to 20 mothers. And here's the 20 students, they're talking to 20 mothers, each with a different color. It cannot mix. It mixes only in a fiber, but then you demultiplex it here again. You know what they use it to split the colors again? Guess what they use? You've learned it in matric, in science. They use a prism. If I put a prism here, I'll split all these colors up again. Did you know that? A little prism. So they combine the colors here and they split it with a little prism here. Very small prism, people. That is a 1 millimeter by 1 millimeter prism. It's so small you can't even see it. They put that prism inside the connector, and they've got 20 cables coming out there, 20 colors. So 20 phones can talk with 20 phones without disturbing each other. You must know all of this. 1, 2, 3, 4, 5, 6, and 6 marks for this picture, how it looks. So 12 marks. 12 mark question. Explain and draw the different fiber coupler types. The optical fiber coupler types. I want them. You draw me these 6 pictures. You put this text here. 1 mark for each text. That's correct. Wavelength multiplexer, wavelength demultiplexer. And nice question. Now we're coming to the 3 and 4 port couplers that I talked in just now. So here they are. Listen, this is just a 2 fibers going out and 1 fiber coming in. We want to combine them. We want to send a signal in there and the same signal join it to that. We'll put some epoxy glue there and then we've got a splitter. There's your splitter. You see now. Also, we can do it like this. We can make a 3-port coupler and we can have a semi-transparent mirror. So light comes in here. There's a little mirror here, a little glass, half a millimeter by half a millimeter little mirror inside the fiber. And we shine the light coming in here also there, so we split it up to another one there. And it goes on. So this is a 45-degree mirror. And this is called a semi-transparent mirror. So it's a 3-port fiber. 3, 3, and 3 on this side. And the light can come in here. Light coming in here will some go up there and some will be reflected. So from the other side, you'll turn the little mirrors in the other direction, in this direction. So that you can communicate 2 ways with this. Then we can put a granite lens. This is the lens here and here, 2 halves of it. So we can take this light comes in here and it goes, all that light goes to that one. Then light comes back here and it will go into that one, into that one. So the incoming light here and the outcoming light here. So this is basically light which is both beams is in 1 fiber and then split it up to 2 different fibers. We use a granite lens for this to align the signal properly. When you align it, you shift it up and down here and you find a focal point there and you find another focal point there. Okay, you can another granite lens, you can put light in here and some of the light will go out, but half the light will go out in that direction. Another granite lens coupler. You don't have to know these pictures, but just note how they work. Then you sort of need to know this one. This one you need to know the formulas. Okay, this is a 4-way coupler, and what we're going to do, there's 1, 2, 3, 4 places where light can come in and go out. So light side. However, at this point, they made a little mirror here where they joined and they joined these 2 fibers together. And now some of the light can go into port 3. Okay, there's 4 formulas you must learn here, and you must know this picture in relation to those 4 formulas. So I'm going to go to the formulas now. It's easier to talk about them. So what you can get the ratio of power into in total power out of the fiber. Right. So this is a 4-port coupler, and we call this losses here the excess loss. It's already in dBs, so it's, well, you must say 10 log 10, okay? 10 log 10, power 1 over power 3 plus power 4, or port 1 over port 3 plus port 4. So this formula, the output is coming in at 1 and going out at 3 and 4. So we can calculate this value and that value going out by using this formula. Okay. Then we can calculate, this is the excess loss. Then they call this one the insertion loss on ports 1 to 4. So it's insertion loss, it's a ratio of the input to a specific output, like 1 and 4. So come in at 1, come out at 4. Come in at 1, come out at 3. So I'll put 1 over 4 there for this one, and 1 over 3 for this one. I'll use this insertion loss formula, going in at 1, going out at 3. I'll use that insertion loss formula there, or coming in at 1, going out at 4. This is port 4, which is the output. Port 3 is also an output. You use this one for the insertion loss. At the end of the day, I want you to calculate these excess loss and the insertion loss. And I'm only giving you the input power. Then you must calculate the rest. Then I can calculate the crosstalk between 1 and 2. Right. So 1 and 2 will tell me how much crosstalk is in that fiber. Crosstalk is sort of how much crosstalk is in channel 3 and in channel 4. So you can use this formula. So it's P2 over P1. And we calculate the crosstalk. If we look at the figure again, the crosstalk is coming in input signal here, and some signal goes out there. Okay, it's a very small signal. So this is a measure of the crosstalk in a fiber. Coming in here and going out at 2. Okay. That's the third formula. The fourth formula, we can calculate the split ratio. Obviously, how much power is split between channel 3 and 4? The split ratio is P3 over P3 plus 4. And this one is not in dB. Do you see? This one is in a percentage. So you can tell me the split ratio is 50%. 50% split ratio will be, this figure, power comes in and it will split 50% there and the other 50% there. However, if the split ratio is 40-60, it means the power comes in, 40% will go on at 3, and 60% will go out at 4. It's the split ratio between the two. So, to recap, we've got insertion losses, we've got crosstalk, we've got split ratio, and then we've got also excess loss. Those 4 things you're going to calculate with this 4-port join here, or coupler. So, sorry, I've got a phone call. I just want to tell him not to disturb me. Hello? I've got a class. Can you call me in an hour's time? Hour and a half. What is it about? Just call me later, thank you. It's not my students. I thought it. Why I'm answering is it might be one of your Opto students. He cannot go log in or so. So normally I don't answer my phone, but I just wanted to know if it's one of my students. I obviously must help him. That's why I'm answering the phone. Normally I don't do that. So this example, people, you must know this example. Go through it, work through this example, and do it. It's a high percentage chance that I can ask you this one. So I can ask you the excess loss, the insertion loss, the crosstalk, and the split ratio. Okay. These are in dBs. You see in dBs, dB, dB. But this last one, split ratio, is a percentage. How much is it split, the ratio? It's in a percentage, not in dBs. Okay, I'm done with it. This is different other ways of couplers. I'm not going to go into that because I've got hundreds of types, you know. And I've got a star coupler. A star coupler is like many outputs and a single input or whatever way. It's a star coupler. Okay, and then I've got a star coupler. I'm not going to do this formula. It's for a star coupler only. You see, there's a star. Well, this is 8 ports to 8 ports, and I join it together. They melt it here. So all these 8 lights here, different colors can mix with those 8 lights. It can be different colors. It can be the same color. They just want to join all together. I think this is when they want to eavesdrop on you. You're talking to number 1, the government at number 2, the police at number 3, the municipality at number 4, and ESCOM number 5. Each one is eavesdropping, and Google is here number 7. You see, there's Google and there's YouTube. That's how you eavesdrop on people. You make a star coupler. You listen what they say. I'm not sure if they do it. People, this is a 32 port by 30 port multi. You don't have to do this example. I'm just showing you. You can even calculate the splitting loss between 32 ports. We're not going to do it. Then there's like, how many is this now? You see, 4 port couplers, lots of them in a grid. This is all fiber. It's a coupler. They make it very small, this thing, and maybe 5 millimeter by 5. It's a 12 4 port coupler. It's a ladder coupler. I'm just showing you. You don't have to know how the couplers can look. They can have all sorts of forms. Optics is a science on its own. It's just like electronics. They can amplify signals. They can divide it. They can add it. They can do mathematical functions. In optics, they can do a mathematical optic computer. They've built it. Né? It doesn't work like a normal computer. It's 1,000 times faster than any PC that you can find today. These optical computers can do a lot of different things. A lot of mathematics optically. And then it's much, much faster. They say the future will only have optical computers. It won't be electronic computers like today. They are just too slow. Okay, just for the interest sake. Optical computers will be the future. Okay, this is, we don't have to know this. I'm just going to skip this stuff. I'm not going to do this at all. Okay, this is interesting one. This is what they do here. They split the light. And this is how they do. That's called a litho grating demultiplexer. All right. So your 3 colors come in here. 1 fiber. Ne? 3 colors come in here. Then I've got little. It's like little prisms there. People, this thing is like a 1/4 millimeter big there. 1/4 of a millimeter. This is small stuff. You can't even see this thing. And then the light reflects off that surface. They can adjust it up and down here. And they can have different colors coming out there. It's a granulate lens. They also use granulate lenses for this. They use granulate lenses for a lot of optical stuff, guys. That's why you must know what's a granulate lens. And that's why you must know what's a 0.25, 0.23 pitch and so on. But this litho grating multiplexer is just a lens with a sort of a prism interface here. And then they can split the colors. That's how they do it. Very clever. This as well. I'm just skipping this. Just the same stuff. Just the same. I'm not going into it. This is really how they do a 4-port connector. They actually sand it down to 50%. You see here until the core touches the other core, and then they join it. It's just don't learn it. It's just a picture showing how they do it. Okay. You don't have to know this. Nothing here. Okay, you must know this stuff. An isolator and a circulator. Most people don't even know what it is in exam. I might ask it. Probability is high. What is an isolator and what is a circulator? People, an isolator is like a diode. An isolator only allows forward light. It blocks backward light. So when you've got a fiber and you don't want backwards light to damage your laser, you put one of these isolators in. Okay. Isolator looks like this. There's a picture for it. Okay, number A is the isolator. So what they do, it's like a diode. What diodes works for copper wires and electricity, né? But isolators don't. There's no current, but the light will only go in one direction. So this isolator will allow light in their direction and in their direction. So the incoming light will come only in their direction and go out there. It cannot come back. So this incoming light cannot come back. It can only go to the number 2. And then it can't go down here because that light only goes in one direction. So from 2, the light comes in here. It cannot go that way, but it can go this way. It can go to number 3. And the light from number 3 can go back to number 1. So this, they use isolators to give direction to the light. So that's an isolator. Okay. Now, sorry, it's isolator is that one, but the circulator is the whole thing, a 3-port circulator. So it will circulate the light over 3 ports. But the isolator is that little thing. It's a diode for light. So it only goes in one direction. So, or they can have a 4-way isolator, a 4-port circulator. Then they put 4 isolators in here and the light will go like in a circular fashion like this, like how my mouse is moving. Okay. You must know what's an isolator and what's a circulator. And here are different ones, and I'm not doing that, and it goes with different colors of light too, and they do a lot of the different Bragg ratings with this. Bragg rating is you get a Bragg laser also, and grating is that thing splitting the colors, that prism. Because there's some problems here, you can do them, but you don't have to hand it in to me. You can do it on your own, 5.1, 5.3, 5.4. I've asked that one in the paper, 5.5, 5.6, 5.7. You can do it on your own, but I don't want to see it. We are done with this one. Was asked 512 was also in that paper, and 513 you can also do, and 514 was also in that paper. Please do them on your own for homework. Do them, and I can ask questions out of them, and that's it. We are done with chapter 5. Do you want to take another 5-minute break? Yes or no?
Yes, please. Yes.
Yes.
Okay, I'll come back in 5 minutes, ne?
Yes, please.
I'll give you 5 minutes. I'm going to stop the recording here, and then we'll do the 3rd recording for the next chapter. And the next chapter will be about lasers, so we'll get there in just now.